Model selection and a generalization. Let us start with the case of learning a Boolean function from examples. In a Boolean function, all inputs and the output are binary. There are 2 to the d possible ways to write d binary values, and therefore with d inputs, the training set has at most 2 to the examples. As shown in table 2.1, each of these can be labeled as 0 or 1, and therefore there are 2 to the d possible Boolean functions of the inputs. Each distinct training example removes half the hypothesis, namely those whose guesses are wrong. For example, let us say that we have x1 equals to 0, x2 equals to 1, and the output is 0. This removes h5, h6, h7, h8, h13, h14, h15, and h16. This is one way to interpret learning. We start with all possible hypotheses, and as we see more training examples, we remove those hypotheses that are not consistent with the training data. In the case of a Boolean function, to end up with a single hypothesis, we need to see all 2 to the training examples. If the training set we are given contains only a small subset of all possible instances, as it generally does, that is, if we know what the output should be for only a small percentage of the cases, the solution is not unique. After seeing n example cases, there remain 2 to the d minus n possible functions. This is an example of an ill-posed problem where the data by itself is not sufficient to find a unique solution. The same problem also exists in other learning applications, in classification and in regression. As we see more training examples, we know more about the underlying function, and we carve out more hypotheses that are inconsistent from the hypothesis class, but we still are left with many consistent hypotheses. So, because learning is ill-posed, and data by itself is not sufficient to find the solution, we should make some extra assumptions to have a unique solution with the data we have. The set of assumptions we make to have learning possible is called the inductive bias of the learning algorithm. One way we introduce inductive bias is when we assume a hypothesis class H. In learning the class of family car, there are infinitely many ways of separating the positive examples from the negative examples. Assuming the shape of a rectangle is one inductive bias, and then the rectangle with the largest margin, for example, is another inductive bias. In linear regression, assuming a linear function is an inductive bias, and among all lines, choosing the one that minimizes squared error is another inductive bias. But we know that each hypothesis class has a certain capacity and can learn only certain functions. The class of functions that can be learned can be extended by using a hypothesis class with large capacity, containing more complex hypotheses. For example, the hypothesis class that is a union of two rectangles has higher capacity, but its hypotheses are more complex. Similarly, in regression, as we increase the order of the polynomial, the capacity and the complexity increase. The question now is to decide where to stop. Thus, learning is not possible without inductive bias, and now the question is how to choose the right bias. This is called model selection, which is choosing between a possible H. In answering this question, we should remember that the aim of machine learning is really to replicate the training data, but the prediction for new cases. That is, we would like to be able to generate the right output for an input instance outside the training set, one for which the correct output is not given in the training set. How well a model trained on the training set predicts the right output for new instances is called generalization. For best generalization, we should match the complexity of the hypothesis class H with the complexity of the function underlying the data. If H is less complex than the function, we have underfitting. For example, when trying to fit a line to data sampled from a third-order polynomial, in such a case, as we increase the complexity, the training error decreases. But if we have H that is too complex, the data is not enough to constrain it, and we may end up with a bad hypothesis. Little h is taken from H. For example, when fitting two rectangles to data sampled from one rectangle, or if there is noise, an over-complex hypothesis may learn not only the underlying function but also the noise in the data and may take a bad fit, for example when fitting a sixth-order polynomial to noisy data sampled from a third-order polynomial. This is called overfitting. In such a case, having more training data helps, but only up to a certain point, given a training set and h. We can find little h, which is from h, that has a minimal training error, but if h is not chosen well, no matter which little h from h we pick, we will not have good generalization. We can summarize our discussion citing the triple trade-off. This is from the results of Dietrich in 2003. In all learning algorithms that are trained from example data, there is a trade-off between three factors: the complexity of the hypothesis we fit to data, namely the capacity of the hypothesis class, the amount of training data, and the generalization error on new examples. As the amount of training data increases, the generalization error decreases. As the complexity of the model class H increases, the generalization error decreases first and then starts to increase. The generalization error of an over-complex H can be kept in check by increasing the amount of training data, but only up to a point. If the data is sampled from a line, and if we are fitting a higher order polynomial, the fit will be constrained to lie close to the line if there is training data in the vicinity. Where it has not been trained, a higher order polynomial may behave erratically. We can measure the generalization ability of a hypothesis, namely the quality of its inductive bias, if we have access to data outside the training set. We simulate this by dividing the training set we have into two parts. We use one part for training, i.e. to fit a hypothesis, and the remaining part is called the validation set and is used to test the generalization ability. That is, given a set of possible hypothesis classes hi, for each we fit the best little hi in capital Hi on the training set. Then, assuming large enough training and validation sets, the hypothesis that is the most accurate on the validation set is the best one, the one that has the best inductive bias. This process is called cross-validation. So, for example, to find the right order in polynomial regression, given a number of candidate polynomials of different orders where polynomials of different orders correspond to hi, for each order, we find the coefficients on the training set, calculate their errors on the validation set, and take the one that has the least validation error as the best polynomial. Note that if we need to report the error to give an idea about the expected error of our best model, we shouldn't use the validation error. We have used the validation set to choose the best model, and it has effectively become a part of the training set. We need the third set, a test set. Sometimes also called the publication set, containing examples not used in training or validation. An analogy from our lives is when we are taking a course. The example problems that the instructor solves in class while teaching a subject form the training set. Exam questions are the validation set, and the problems we solve in our later professional life are the test set. We cannot keep on using the same training validation split either, because after having been used once, the validation set effectively becomes part of training data. This will be like an instructor who uses the same exam questions for every year. A smart student will figure out not to bother with the lectures and will only memorize the answers to those questions. We should always remember that the training data we use is a random sample, that is, for the same application. If we collect the data once more, we will get a slightly different data set. The fit H will be slightly different, and we will have a slightly different validation error. Or if we have a fixed set which we divide for training, validation, and test, we will have different errors depending on how we do the division. These slight differences in error will allow us estimate how large differences should be to be considered significant and not due to chance. That is, in choosing between two hypothesis classes Hi and Hj, we will use them both multiple times on a number of training and validation sets and check if the difference between average errors of Hi and Hj, where this one is little hi and little hj, is larger than the average difference between multiple hi. In Chapter 19, we discuss how to design machine learning experiments using limited data to best answer our questions. For example, which is the best hypothesis class, and how to analyze the results of these experiments so that we can achieve statistically significant conclusions minimally affected by random chance.